preferably done right. Okay, come on, recording. Okay. It's kind of fun, even though I'm just doing my job from a different campus today, so it's still a work day. But because I'm traveling to do it, I feel like I'm on vacation. It's because I'm in travel mode or something. I should do this more often. Okay, now, so here we are. So solution of the first order ODE. Okay, so y prime, y plus b of t is, all right, a solution of a homogeneous, so this is an inhomogeneous ODE because of a b of t. So a homogeneous solution and the particular solution, and we only care about the, stop it. I gotta figure out what key sequence I'm hitting that launches the music app. All right, so that's a homogeneous part, which we don't care about, and the particular solution is the integral from 0 to t, and I'll put the e to the lambda t outside. Okay. All right, and okay. So just keep morphing the particular solution. All right, and then replacing B with a Taylor expansion. Okay, and then I have S to the, stop it. That's the third time it's happened today. Okay. All right. And then as before, just doing some rearranging, pulling out what I can from the integral. A whole lot easier to do in this setting where I can just copy and paste. Okay. Okay. Let's see, don't need these brackets anymore. Okay. And then making a U substitution, which I'll make note of here. Okay. Okay, and then this is So ds is going to be, I'll make a note of that here. Okay, so now I'm going to have a factor of 1 over lambda out here. Okay. Actually, I'm going to take the j factorial and move it into the braces. So everything in the braces is what I really want to work with. Okay. So that happens because of the U substitution. Okay. And then I want to make this U to the j. So I need a lambda to the j in here. Therefore, I need a lambda to the j in the denominator out here. So now I'm going to have lambda raised to the j plus 1. And then here we have U to the j. Okay. Now, before I go any further, I have notes off to the side. Okay. Now, one thing that I should have done last time, because right now, so far, this is consistent with everything I did before. But now I need to do something a little different. If you're not sure where something comes from, you are welcome to interrupt and ask me about that. Okay, now, because notice here we have lambda t and lambda t. But here I have just lambda raised to a power. So I want to have lambda times t raised to that power. So I can do that. Provided I multiply by t to the j plus 1 as well. I'm going to put that out here. Okay. So now all of that is set. Okay. Now, as a shorthand, so notice I have lambda times t in a few places. So I could create a new variable to replace that with, just to shorten things. Okay. Okay. Oh, I guess I didn't need to copy these the information about the U substitution every time. All right, so I'll define W equal to lambda t. Okay. Now, as before, j equals 0 case. So we'll just take a whole expression inside the braces. And now specialize it for a case of j equals 0. So we have j factorial is 1. We have just w by itself. Okay, e to the w, and then u to the j will go away. That's just 1. Okay. So now the integral can be worked out. and that turns out to be minus e to the minus u with the limits plugged in. Okay, so the integral is just that. But now we simplify everything, and I get, fourth time. Dang it. Okay, so e to the w minus 1 up top, and then just w down below. Okay. And I'm going to define that to be phi1 of w. So in general, the way I'll define these phi functions is just this whole expression here that I had before. Okay. And this is for 0, 1, 2, and so forth. But I also have, so this will define phi1, phi2, phi3, etc. But I also have phi0, and that's just a plain old exponential. Okay. Right. So, any questions up to this point? Okay, so we have the first two phi functions, simple expressions for them. But now we have this nasty one for any others. So of course we want to simplify that. So this is where integration by parts comes in. Okay. So what we get here is u to the j, and then minus e to the minus u, with limits 0w plus okay, so then I have j u to the j minus 1, then e to the minus u. Okay. All right, so at least that's how the integral is handled. But the phi function is this integral times some things. So now if I include the rest of that, okay. So I'll take this and then just take the integral part. Oh, actually, I should have completed this, actually plugged in the limits. So like if I plug in u equals 0, then the term of the lower limit won't contribute anything. So then I'll have minus w to the j, e to the minus w, plus, and then everything else. Okay, so that is what I want to substitute in here. Okay. Okay, now I got a bit of distributing to do. What was that? Okay, so I'll just take all this stuff. Okay, and now since simplifying, okay, the exponentials cancel. This cancels with most of the w's down below. So now what I have left is minus 1. What happened? Okay. Over the j factorial is still there. And then I just have w by itself. Okay. All right. Plus, so when I simplify this, okay, so j over j factorial, so that will simplify to j plus 1 factorial down below. Okay. And then I'm going to take one of these factors of w and set it aside. And then I have a remaining wj over here. So now if I compare this part to here, that's just the previous previous Phi-function. Okay. Alrighty. One thing I'm checking here is if everything is as it's supposed to be. I believe so. But I thought that last time too. Okay, so now I have a pretty simple recurrence to define all these Phi-functions. So I did j equals 0 before. So let's see what happens when j equals 1. So that means phi2. So that's going to be equal to minus 1 over just 1 times w plus w for phi 1. And we know what that is. Okay, so that's filled in from before. So we want a common denominator. So I need to multiply this by w over w, and we get e to w minus 1 minus w. So this comes from here, all over w squared. Okay, so that worked out as intended. But I'll feel a little more confident about this if the next one works too. So for j equals 2 case, we have phi 3. So now I have 2 factorial. So I'll have a 2 down here times w. Okay, and then I have phi 2 of w here. Okay. And now I can fill that in. Okay. So now what I'm going to do is I want a common denominator again. But what I'm going to do is, you'd think a common denominator I would want is 2w cubed, but I'm actually not going to do that. Instead, okay, sorry, something weird happened in my Teams window. Okay. So I'm going to put a w squared up here, and then I'll w cubed down here. If I'm going to take the 2 in the denominator and move that into the numerator as a factor of 1/2. Okay, so then when I put all this together, I'm going to have in the numerator e of w minus 1 minus w minus the next term from the familiar Taylor expansion. Sorry, LaTeXing went very badly all of a sudden. Let me fix this. W squared all over w cubed. Okay, so sure enough, it worked out as planned. So yes, after 2 class periods, I finally got it right. So in general, phi j plus 1 is equal to 1 over, okay, so j plus 1. All right, so I have that for denominator, and then I have e to the w minus sum, okay, so if I subtract off terms up to power j in the Taylor expansion. Okay. So that's what we have here. So for instance, in case j equals 2, I subtract off first 3 terms of a 1, the w, and then w squared over 2. And then divide by w cubed. Okay. So now, finally, I have this expression for a particular solution of the ODE. So it's the jth derivative of your right-hand side, your source term b at 0, times t to the j plus 1 times phi j plus 1 of w, but w is lambda t. So I just include that in there. Okay. So I have this way of expressing a particular solution. So now, if I could apply the same idea to the system of ODE, so like y prime is equal to a y plus some vector valued function, the source term b of t, where the particular solution in that case will have the same form. All right, so here we're taking a derivative with respect to time of each component of the function b of t evaluated at 0, and then the same factor here. And now we have a phi function of a matrix, so a matrix A times T. Okay. So now, so at least now we have a formula for a solution that does not require evaluating integrals, because the integrals have already been evaluated for the integration by parts. We just need these derivatives. And what actually led me to cover this in the first place is that this approach to expressing a solution of a system of ODEs recently played a role in my research, where I would use like the first few terms of this to to express an approximate solution. Okay, so if I start, instead of sum equals j equals 0 to infinity, as if I do like j equals 0 to k, to obtain a approximate solution where the error is yeah, middle of a class. Okay. Not sure what that was. Okay. Actually, it's t to the k. Yeah, local truncation error. Okay, let me make sure I have this right from an example I did. because one time, like if for instance, if I stop at k equals 0, okay, so it's t to the k plus 1, which makes sense because that's the factor that we would have in this case. So the error would come from the next term, like the first term is excluded from the approximation. Okay. So if all you want is an approximate solution, then you can just use one of these Phi-functions. If you're already approximating a matrix exponential, which you need to do for the homogeneous part of a solution, then there's not much extra work to handle the particular solution also, because this is closely related to matrix exponential. Although, in the definition of a Phi-function, for instance, with Phi1, we have so you have e to the at minus identity, and then here we're dividing by a. And we can't really divide by a. You'd be multiplying by a inverse. So there is an inversion that has to happen, unfortunately. So that's so accounting for a source term in the solution of a system of ODEs from a numerical standpoint is a bit more work because you're having to solve a system of equations involving this matrix A. Okay. So, but yeah, so you could truncate this at whatever point you want to at least have an approximate solution. Okay. So made it to the end, and at least everything went smoothly this time. So in the 8 minutes we have left, any questions about anything, homework, or whatever? I've had very quiet classes today. I still have one more to look forward to.
Thanks, Dr. Lambert.
Okay, so all right. Well, if you got nothing, then we're done. Until 5:30, that is.
All right, thank you.
Yep.
See you later.
Or sooner.